Hello, it's Peter here with the physics of projectile motion. Let's, by way of introduction, talk about some stages of complexity and what's in the toolbox, and then I'm going to make a few big picture comments at the end. I think it's helpful to realise that you kind of can ramp up levels of complexity. So first thing you need to be able to do is just stage one, if you've got something and you drop it, and it lands on the ground, just a vertical drop, or maybe something being thrown up vertically, coming down in the same line. So it's really one-dimensional motion. It's actually not projectile motion because it's single dimension. But this is the starting point to be good at this kind of vertical up and down. So stage one. Next level of complexity is when you do make it two-dimensional, and you say I've got a table and I've got a ball and I push the ball off the table, and now it goes through a projectile motion path, two-dimensional path. So that's kind of the next step up. This has a name. This is often referred to as horizontal launch. Stage three is your classic projectile motion, say kick a soccer ball, and it goes through the full parabolic path like that and lands there. And you might say be given the initial velocity here, v, and be asked to find how high does it go or how far does it go, things like that. After that, you will be asked to do examples where there's different levels. So in stage three, it landed at the same level as it started, but now the next step up is to say different levels for start and finish. Might look like that, might look like this. Okay, so that's kind of the levels, and if you are struggling here, you might want to go back and make sure you can do that, or here's a problem, and go back, but realize that you can kind of work up to the more complex questions. What have you got in the toolbox? Well, of course, you've got equations of motion from studying straight line motion at an earlier time, and we've got two dimensions, so we've got vertical only, and we treat them separately. Vertical and horizontal, that is. Equations of motion. Well, I'll give you three, and I realise that there's others, but I find that these three do the job, and others are really a combination of these anyway. So there's the most common three. When you go to horizontal motion, you're focusing just on the horizontal part, then all you need is that velocity is displacement over time. So there's your equations of motion. Let's notice some things about these. I think it's helpful to notice that in these equations and in any others that apply, there's only 5 variables. That's it, no more, just those 5. Displacement, initial velocity, final velocity, acceleration, so A, acceleration, and time. Here's a tip for figuring out which equation you need to use at any given time. Notice that each equation has got 4 variables in it, and different ones, a different combination of variables in each of those 3. So let's classify them according to what's missing. This one, there's no displacement in the first one. This one here, there's no final velocity in that one. This one, there's no time. So this can help you choose which equation you need, because in any question you would be given, say, typically you would be given 3 of the 5 and be asked to find one of the missing ones. So you can say, well, I've been given these three and I've been asked to find, well, you won't be asked to find A, that's 9.8. So you're given, say, S, U and A, and you're asked to find V. So you'd say, well, T's not in what I've been asked for, so I'll use this equation here because then I don't have to worry about T and I can solve it for V as I've been asked to. So that's useful to observe. I'll just finish that off by listing. I'm just going to make sure these look separate. Vertical, horizontal, and here we've just got S, V and T. Okay, well, just as a little aside notice, a little exercise for you, because there's constant velocity here, acceleration is 0 horizontally. If you look at these three equations, put a 0 where A is, you end up with V equals U. Well, we know that, it's constant velocity. S equals ut. Well, that's that. S equals ut. Just rearrange it and you get S equals VT. And cover A up because it's 0, and V squared equals U squared. So it's really using the same equations, but A is 0. So that's one thing you've got in your toolbox. And another thing in the toolbox is your trigonometry skills. You need to be able to use sine, cos and tan. You need to have that as a skill. The way it shows up in projectile motion is, for instance, you're given an initial velocity, like I mentioned here, be some value at an angle, and you need to be able to turn it into components. So a horizontal component of that and a vertical component. So you'll need sine and cos to be able to do that. In other situations, you might be asked to say, what's the final velocity? And you'll calculate final vertical, you'll know the horizontal velocity. So in that case, you're adding vectors to figure out the final velocity. So it looks something like this. Horizontal's that much, vertical's that much. Add them together and get an answer. You definitely need trigonometry to find that angle because that's part of the answer. So that angle there, you'd need inverse tan or something that's going to help you there. The magnitude of the addition of the two vectors, you could use Pythagoras or you could use trigonometry to do that. So that's the toolbox. Some comments about projectile motion generally. If you're like me, you're thinking, well, what about air resistance? And fair enough, because you know that air resistance is significant. We keep it simple. We say ignore air resistance, at least in exam type questions. I know in some practicals, some experiments, some of you would have brought in air resistance. But when it comes to calculations, you can ignore air resistance. To bring it in is quite complex. And after all, in a lot of situations with a reasonably dense object, not going too fast, these equations are very useful, very good approximation, good predictors, without worrying about air resistance. So, yes, it's there, but we're ignoring it in high school physics. So, air resistance, be assured that it is being ignored, and that's okay. There's other air effects, as just mentioned, so things like Magnus force spin, the spin of an object, or aerodynamic effects from the shape are also ignored. So other air effects are ignored. Projectile motion is actually just about one force. So this sort of path what you're doing is saying something's been set in motion somehow. You don't even need to tell you how. It's in motion, it's got this velocity and so on. And it's really about saying what happens to this thing given that there is one force, one vertical force. I'll try and draw that vertical. The force of gravity is the force that acts, and that's what this topic's about. So that means that you don't have to worry about what forces are involved in getting the thing going. Okay, don't sit there thinking, well, do I have to calculate something about what launched it? No, you don't. It's in motion, worry about gravity. It also cuts out any forces at the end, the bang at the end, the catch or the hitting something. That isn't part of projectile motion. It's purely that path through the air with that single force of gravity acting. So that's introduction. There are stages of complexity. You need the skill of equations of motion, of trigonometry, and then there's these comments that will kind of put a boundary about what you need to worry about. So introduction to projectile motion.